guys, welcome to my YouTube channel. My name is Ranjiti. I am pursuing BTech in Sri Venkateswara College of Engineering. Subject is Mathematics 2. Topic is Application of Area and Volume in Integration. Subtitle Exploring Calculus Concepts in Real World Scenarios. Definition: Integration in calculus involves finding the accumulation of quantities over a continuous intervals. Explanation: Integration breaks down complex shapes or functions into small pieces, calculate their contributions, and sum them up to find the total or cumulative effect. Example: to find a total distance traveled by an object given its velocity function f of x over a time interval a comma b. We integrate the velocity function over that interval. Total distance is equals to integrate limits from a to b f of x into dx. Slide 3. Area under a curve. Definition: the area under a curve is total area of a region bounded by the curve on a given interval of the axis. Explanation: we use integration to find the area under a curve. This involves dividing the region into small rectangles along the x-axis, calculating the area of each rectangle, and summing up all these areas. As the width of each rectangle approaches 0, the sum converges to the actual area under the curve. Example: consider the function f of x between the 2 points a and b on the x-axis. The area under the curve is given by the definite integral area equals to integrate from limits a to b f of x into dx. Area between curves. Explanation: to find the area between two curves, we calculate the area between each curve and the x-axis separately and subtract the smaller areas from the larger one. This done by finding the difference between definite integrals of two functions over the same interval. Example: if we have two functions f of x and g of x, with f of x is greater than or equals to g of x, or a is less than or equals to x and less than or equals to b, the area between the curves is given by area equals to limits from a to b f of x minus g of x into dx. Volume of revolution. The volume of revolution is the volume obtained by the rotating a region bounded by a curve around a line, usually the x-axis or y-axis. Explanation: we use integration to find the volume of revolution. This involves slicing the region into thin disks or cylindrical shells perpendicular to the axis of rotation, calculating the volume of each slice and summing up these volumes using definite integrals. For example, for a region bounded by the curve y equals to f of x rotated around the x-axis, the volume of revolution is given by v equals to pi of integrate limit from a to b f of x whole square into dx. Volume by cross section. Explanation: we give integration to find the volume of a solid by cross section. This involves slicing the solid into thin slices perpendicular to the fixed axis, calculating the area of each slice and summing up these areas using definite integrals. Example: for a solid with cross sectional area m perpendicular to the x-axis, the volume is given by v equals to limit from a to b a of x into dx. Application in physics. Explanation: integration is extensively used in physics to calculate the area and volumes related to motion, work, energy, and other physical quantities. For example, integrating velocity with respect to time gives displacement, and integrating force with respect to displacement gives work done. Applications in engineering. Explanation: integration plays a crucial role in various engineering disciplines including civil, mechanical, and electrical engineering. It is used to analyze structures, determine stress distribution, calculate fluid flow rates, and solve many other engineering problems. Applications in economics and finance. Explanation: integration is employed in economics and finance to model and analyze various economics and financial phenomena such as production, consuming investment, and risk management. It helps in calculating areas representing economic quantities and in solving differential equations, modeling economic systems. Example: calculating consumer sulfurs involves finding the area under the demand curve and above the market price, which is obtained through integration. Conclusion recap: summarize the key applications of area and volume in integration across different fields, including mathematics, physics, engineering, economics, and finance. Importance: emphasize the significance of integration in solving real world problems, advancing knowledge, and driving innovation in various disciplines. Thank you. Do like, share, and subscribe.